k-nearest neighbors, KNN imputation estimates missing values based on the similarity of neighboring data points, maintaining relationships in the dataset. This method is particularly useful when dealing with nonlinear patterns. Another advanced approach is multiple imputation, which generates several plausible datasets with different imputed values and combines the results to account for uncertainty. The impact of unhandled missing data on model performance can be severe. Studies have shown that datasets with significant missing values can experience a 20% or more decrease in predictive accuracy. This loss occurs because models trained on incomplete data are more prone to biased estimates, misclassification errors, and reduced generalizability. For example, in healthcare, missing critical patient data can lead to incorrect diagnosis predictions, while in finance it may distort risk assessments. Addressing missing data requires not just technical expertise, but also domain knowledge to understand the potential reasons behind the gaps. Best practices for handling missing data include conducting thorough exploratory data analysis to identify patterns, leveraging domain expertise to understand the causes, and choosing imputation techniques that preserve the underlying data structure. For example, if a marketing dataset shows missing purchase history for some customers, imputing these values based on their behavior patterns, like browsing data, might provide a more accurate estimation. Ultimately, the key to managing missing data is to strike a balance between simplicity and accuracy. While straightforward methods like mean imputation may suffice in some cases, more advanced techniques like KNN or multiple imputation are essential for maintaining the integrity of complex datasets. By effectively addressing missing data, you can ensure your machine learning models are robust, reliable, and capable of delivering meaningful insights. Classification algorithms are at the heart of many modern applications, powering innovations across industries by solving real-world challenges with precision and efficiency. Let's explore how these algorithms are transforming healthcare, finance, and marketing. In healthcare, classification algorithms are saving lives and improving outcomes through early detection and personalized care. For instance, support vector machines, SVM, and decision trees are widely used to predict diseases based on patient data. Algorithms can analyze medical images to classify tumors as benign or malignant, achieving accuracy rates exceeding 90%. By automating diagnosis, these models help doctors make faster, more informed decisions. Another impactful application is patient risk assessment, where classification models identify high-risk individuals for conditions like diabetes or heart disease. By analyzing patterns in patient records, these algorithms enable proactive interventions, significantly improving early detection rates. Studies have shown that such systems can enhance detection rates by up to 30%, which translates into better health outcomes and reduced costs. The financial sector relies heavily on classification algorithms to assess risks and detect fraud. Credit scoring models powered by logistic regression or random forests analyze historical data to predict an applicant's credit worthiness. With accuracy rates of around 85%, these algorithms ensure smarter lending decisions by minimizing the risk of defaults. Fraud detection is another area where classification algorithms excel. By leveraging techniques like random forests, banks and payment platforms can identify fraudulent transactions in real time. These models analyze transaction patterns to detect anomalies, helping to reduce financial losses by up to 50% in some cases. This is particularly critical in an era where digital transactions are growing exponentially. In the world of marketing, classification algorithms enable businesses to better understand their customers and tailor their strategies. Customer segmentation uses classification techniques to group customers based on purchasing behavior, demographics, or engagement. For example, clustering algorithms identify high-value customers, helping businesses target them with personalized campaigns. This approach has been shown to improve marketing ROI by as much as 20%. Another powerful application in marketing is churn prediction. By analyzing historical customer data, classification models can identify individuals likely to stop using a service. This allows companies to implement targeted retention strategies, reducing customer loss rates by 15% or more. For example, a subscription service might use these insights to offer special discounts or personalized outreach to high-risk customers. The power of classification algorithms lies in their ability to transform raw data into actionable insights, making them invaluable across industries. Whether it's detecting diseases earlier, mitigating financial risks, or crafting targeted marketing campaigns, these algorithms drive efficiency and innovation. As machine learning advances, we can expect even more sophisticated applications that reshape how we solve real-world problems. While classification algorithms are powerful tools, they also come with their own set of challenges that can hinder performance and reliability. Let's dive deeper into the common pitfalls and obstacles encountered in building and deploying classification models. Overfitting occurs when a model becomes too specialized to the training data, capturing noise and outliers instead of the underlying patterns. This results in poor generalization to unseen data, leading to high variance and unreliable predictions. Think of it like memorizing a textbook for an exam rather than understanding the concepts. Great on the training set, but ineffective in real-world scenarios. How to address it? Techniques such as regularization, cross-validation, and pruning in decision trees can help mitigate overfitting. Gathering more data and reducing model complexity are also effective strategies. At the other end of the spectrum is underfitting, which happens when a model is too simplistic to capture the underlying patterns in the data. This leads to high bias, poor accuracy, and suboptimal performance on both training and test datasets. Essentially, it's like trying to use a hammer to fix every problem. It's not nuanced enough for the task. How to address it? Using more complex models, adding features, or reducing noise in the data can improve a model's ability to learn effectively. Noise in datasets refers to irrelevant or random errors that can mislead the model during training. For example, mislabeled samples or inconsistent data entries can create confusion, leading to subpar model performance. Imagine trying to learn a new language from a book filled with typos. It slows you down and reduces understanding. How to address it? Robust pre-processing techniques such as outlier detection, feature selection, and data cleaning are essential to minimize noise. Additionally, visualizing data distributions can help identify potential anomalies. Imbalanced datasets occur when one class dominates the others, causing the model to favor the majority class while neglecting the minority. This is especially problematic in scenarios like fraud detection or disease prediction, where the minority class holds critical importance. How to address it? Techniques like resampling, oversampling the minority class, or undersampling the majority, generating synthetic data using methods like SEMOT, and using algorithms tailored for imbalanced datasets can help achieve better balance. Selecting the right features is crucial for building effective classification models. Irrelevant or redundant features can introduce noise, increase complexity, and degrade performance. Conversely, missing out on key features can result in an incomplete understanding of the data. How to address it? Employing feature selection techniques such as recursive feature elimination or regularization methods like lasso can help identify the most impactful features. Additionally, tools like shape values can provide insights into feature importance. Each of these challenges represents a critical aspect of classification model development, requiring thoughtful strategies to overcome. By addressing these obstacles, we can ensure that models are not only accurate but also robust and reliable in real-world applications. Remember, the success of a classification model isn't just about the algorithm, it's about how well you prepare your data and adapt to the challenges along the way. The field of classification algorithms is evolving at an unprecedented pace, driven by advancements in computational power, data accessibility, and the growing complexity of real-world problems. Let's explore some of the most promising trends shaping the future of classification. The rise of deep learning has revolutionized classification tasks, especially in areas like image and sequence data. Architectures such as convolutional neural networks, CNNs, and recurrent neural networks, RNNs, have significantly improved the accuracy and efficiency of models. Transfer learning is another game changer, allowing pre-trained models to be adapted for specific tasks, reducing training time and resource requirements. In real-world applications, this means tasks like medical image classification, where accuracy is paramount, can now achieve results that were previously unimaginable. AutoML frameworks simplify the process of selecting the best classification algorithms and tuning hyperparameters, making advanced techniques accessible even to non-experts. By automating labor-intensive tasks, AutoML reduces development time and effort while still delivering high-performance models. This democratization of machine learning allows businesses and organizations with limited technical expertise to leverage classification algorithms effectively, driving innovation in fields ranging from healthcare to finance. As classification models become more complex, interpretability is increasingly critical. Explainable AI, XAI techniques shed light on how models make decisions, fostering trust, accountability, and regulatory compliance. This is particularly crucial in industries like finance, where understanding why a loan application was approved or denied is as important as the decision itself. For organizations, embracing XAI ensures transparency, enabling stakeholders to confidently rely on AI systems for decision-making while meeting ethical and legal standards. These trends point to a future where classification algorithms will be not only more powerful, but also more accessible and understandable. Whether you're a data scientist, business leader, or technology enthusiast, staying ahead of these developments will help you harness the full potential of classification in your work and industry. As we come to the end of our journey exploring classification algorithms, let's tie it all together. Classification techniques are the backbone of countless applications. From identifying fraudulent transactions to predicting customer behavior, here's a high-level recap of the most important algorithms and their strengths: decision trees. These models use a tree-like structure to split data based on feature values, making them highly intuitive and interpretable. They excel in scenarios requiring clear decision paths, such as medical diagnostics or loan approval systems. Support vector machines, SVM. SVMs are robust classifiers that find an optimal hyperplane to separate classes, especially in high-dimensional spaces. They are particularly effective for tasks like text classification and bioinformatics, where precision and handling complex boundaries are critical. Random forests. By combining multiple decision trees, random forests create an ensemble method that reduces overfitting and increases accuracy. This makes them reliable for diverse datasets, from predicting housing prices to analyzing financial trends. Neural networks. Neural networks, especially deep learning architectures, are unmatched in handling large and complex datasets. Their ability to uncover intricate patterns makes them indispensable in fields like speech recognition, image processing, and natural language understanding. Logistic regression. This fundamental algorithm remains a go-to for binary classification problems. Its simplicity and interpretability make it highly suitable for structured data sets in applications such as credit scoring and medical diagnostics. Every algorithm has its sweet spot, and the key to success lies in understanding your problem domain, the nature of your data, and the trade-offs between accuracy, interpretability, and computational efficiency. Whether you're designing an AI system, analyzing customer behavior, or tackling complex research challenges, these tools empower you to make data-driven decisions with confidence. The future of classification algorithms is bright, and as you integrate these techniques into your projects, remember, they're not just about predictions. They're about transforming raw data into actionable insights that drive innovation and progress.